Hi everyone. So just in case the Zoom meeting doesn't work, I decided I would record these slides and post them. So anyway, let's hope we don't need them. So in the first half of today's lecture, we'll briefly review the basics of modeling in hydrology. Aside from the web link and the list of resources below, the three papers listed there and provided on Moodle provide some inspiration for the lecture materials. Cleams provides a witty critique of modelling and how models are often misused in place of actual observational data. Praskovics and Chang provide a very competent review of runoff models and modelling procedures for basin scale impact and development assessments, while Flugel presents the first paper outlining the widely used hydrological response unit concept in modelling, and we'll overview that later on. Now, you're not going to be evaluated on the materials in today's lecture. However, there is a good chance that the concepts of hydrological modelling will be addressed, at least superficially, in some, if not all, of your class presentations, so it's good background. And of course, modelling would have been a significant component in the team project had that gone ahead. So this would have been relevant and definitely an important part of advanced and applied hydrology. In the second half of today's lecture after the break, Craig, Celeste and Maxim will each give a 15 to 20 minute conference style presentation discussing some of their recent works. So today is the last lecture where I'm in the driving seat. In next week's final lecture, it will be over to each of you to give your presentation, so we're very near the end of this course. Before then, however, I'd just like to remind you that I need your project reports. Thank you for those that have sent them in already. And your presentations one evening before the presentation, so preferably next Sunday or before. And then after that, the essays. So yeah, as I said, very close to the end. So on this slide here, I have listed Santayana's quote, as did Wittliem's in the paper that I've given you to read. Because it serves to illustrate that we rely on our individual or communal observations and memory to make good decisions. The original intention was to suggest that we need to pay attention to history, though the general notion could be applied to any situation where you have imperfect observational data or none at all. The somewhat cheeky addition at the bottom serves to indicate that even if observations were not made, a model can be used to plug the gaps for us, and we'll see that as the presentation goes on. So in the course so far, we've dealt with modeling in a rather implicit as opposed to explicit fashion. For example, Extended Labs 1 to 3 have provided insights into the modeling process and introduced methods for certain types of applied hydrological analysis. The team project was also set up to force you to tackle two types of data modeling: frequency analysis and flood inundation modeling. Whereas in this lecture, we're bringing everything together to understand some general model attributes and many of the model types and constraints inherent in hydrological modeling. At the end of this lecture, you should better appreciate that everything we do in hydrology either helps us create, apply, or learn from models, but models are never perfect. They are a tool for understanding, and like any tool, you need the right one for the job at hand. And any tool can always be improved. So the outline that you can see here will guide the lecture for today. We'll start off by looking at some general model attributes. We'll use some examples. We'll move then into different types of models in hydrology, such as lumped and empirical, or distributed and physical. Then we'll look at some concepts of scales, space and time. We'll also examine some of the constraints inherent within modeling and data availability and data quality issues. And then finally, we'll look at some of the steps to setting up and running a model in different types of environment. So with this slide, this is where we would normally stop and have some discussion, share some ideas. However, as I'm in my basin narrating this, I'll just keep going. So what is a model? Well, in a nutshell, models represent a simplification of reality. But let's look at this quotation taken from the website that's linked there. A model can come in many shapes, sizes, and styles. A model is not the real world, but a human construct to help us better understand real-world systems. In general, all models have an information input, an information processor, and an output of expected results. So common to all models then is the notion of processing or manipulating some input material or data to produce a desired output. So check out the link and you'll be able to find a little bit more information there. So in this slide, I think it's probably fairly obvious which is reality and which one is the model. But here I decided to have a little fun with the modeling examples, and as this is a science course, I've drawn inspiration from one of my son's grade 1 science fair projects. I guess maybe he did have a little help from his parents, as he was able to use thermography to examine the thermal properties of different roof types and coverings. So within this image, can you detect the different types of models that are present? Now again, this would be a topic for discussion, but as I'm recording this, I'll just ask you to think about this for a little while. Now there's one obvious model there. You can see the physical scaled down representings of buildings with black and white roofs and green vegetated roofs and then an open soil roof. So those were the models that are used in his experiment. But maybe look at what's on the poster board there. And you'll see other model representations of data, of images, different plots of numerical data. And so in their own way, they all represent different types of models. So from those, which are the most similar to the kind of models that we might use in hydrological simulations? So here we see a close-up of some of those graphics displayed on the poster board. And while nothing you see here represents the kind of phenomena we would typically address in a hydrological simulation, immediately we find the tables of values, the histogram, and the line plot to be familiar data representations that we have encountered in all of our hydrological labs so far. So the common element here is quantitative or numerical modeling. Now, in this case, the numerical plots we are looking at are in fact observations or summaries of observed temperature, and so in many ways are more analogous to the kinds of data input we may use in a hydrological simulation. However, these numbers are also the result of some behind-the-scenes numerical modeling process. As thermal imaging systems do not directly observe temperature, they record a brightness value that is then converted to surface temperature using a lot of additional information. So while the numerical processes are different, the conversion of a brightness value into temperature has some similarity to the conversion of observed rainfall into a modeled runoff output. Now, whether an airfix kit or a global economic forecast, there are common requirements needed in the development of any model. Availability of material, data, information that can be processed or manipulated. Given the model is a simplification of reality, we must make choices over where to simplify. This may be constrained by input availability or the construction of the model itself. Also, for practical earthly purposes, we can assume reality is unbounded in space and time. Models, however, do not appear out of thin air, and they can only represent a finite spatio-temporal domain. Consequently, constructing a model or setting it up may require some blending or extension beyond the edges of the domain of interest to enhance the model realism, and this is known as defining our boundary conditions. Models usually have a particular purpose, and when used or applied outside the intended domain, their usefulness breaks down. So now, in your own time, consider these modeling requirements and try to apply the previous examples of an airfix plastic kit or to the HECRAS hydraulic model that we've looked at previously. So we'll look at those over the next 2 slides. Okay, so this is where we would normally have a group 5 where you'd all go off and into your groups, have a discussion and then report back to the class. Instead, let's just look at what we have on the slide here. We've got some plastic mold with components of the model. We have a finished model of an airplane. This is our airfix kit, and then we have some glues and some paint pots there. So given this, what are our available inputs into this model? What are some of the simplifying assumptions? What are some of the boundary conditions? And what's the range of application? So I'd like you to spend a little time now thinking about that, and if we have the opportunity, we'll discuss. Okay, so now the same exercise again, but now with the HECRAS water level modeling environment. So available inputs, simplifying assumptions, boundary conditions, range of application. Now that we have looked at some of the general model examples and considered some basic requirements, let's define some general classes or types of models. If you Google model classifications, you will find many different types. However, most models can generally be said to fall primarily into one of the above classes, though models can also belong to more than one of these classes. A conceptual model helps us understand some aspects of reality or their interactions. Any form of modeling effectively requires a conceptual model as a first step. A demonstration model is an act of doing something to otherwise simulate or describe reality. It could be a lab experiment, such as when using a scaled flume to study wave action. All visualizations, whether 1, 2, 3, or 4-dimensional, are a model of something or some event. In hydrology, we are mostly concerned with mathematical models, which can be equation or statistically based, though most models, even hydrological, are a blend of multiple different types. So, if you think back to our introduction to hydrology lectures, we may not have explicitly discussed hydrological modeling, but can you think of any models that guided our discussion? In particular, there was one model that referred to throughout the course. Well, all the model types noted were used in lectures and labs, but conceptual and mathematical constructions of the hydrological cycle and water balance were the building blocks of all material presented. In particular, the water balance equation was presented as a simple mathematical model representation of the Earth's water cycle. And of course, here we have a visual or illustrative model of the water cycle, which is itself a conceptual model of the Earth's hydrological system. So, as was introduced in Introduction to Hydrology, the basic unit in hydrology and hydrological calculations is often the watershed. So at the top of this slide, we see a conceptual graphical model illustrating hydrological inputs of precipitation and outputs of runoff, all bounded by the extent of the watershed. Below this, we see a systems diagram that could be used to represent the same processes whereby some mathematical algorithm or resistance term relates the precipitation input to the runoff output. You may recall the unit hydrograph as such an example. Consequently, many hydrological models concentrate on relating inputs to outputs within the spatial extent of a watershed. The nature of the mathematical description of these relationships can be very simple or highly complex. So, if all models are some variation on the watershed water balance that we now know so well, how do the models introduced in advanced hydrology differ from intro to hydrology? Well, basically it's because hydrological processes are now represented in an integrated framework of components, which we can refer to as a systems approach. Here we see a conceptual visualization model of how we've dealt with hydrological principles in the advanced hydrology course so far. In this conceptualization, we see the linkage between outputs of one model component and the inputs of another. For example, Lab 1 dealt with elements of the far left input side of the overall model, while Lab 2 addressed the design phase of a hydrometric study to obtain basic input and output data. Lab 3 developed watershed or floodplain parameterization skills, whilst the team project examined floodplain and inundation components of the modeling workflow. And so hopefully with this diagram you can see how all of the components fit together. Similarly, any individual model component, such as the watershed extent and flow routing components, can also be subdivided into constituent elements. Here we see a standard GIS process that you should all be familiar with by now. I'm sure you can all recognize this as the watershed delineation workflow, which is itself an example of a modeling process. And here we have yet another GIS routine to serve as an example. This time an energy balance snow or ice melt model. Here each term in the melt equation is represented by raster surfaces, which are updated periodically through time. As long as the basic terrain grids are available, such an energy balance model is relatively easy to construct and run. However, this model will only estimate melt. It will not estimate flow routing. We will look at flow routing shortly. However, what happens at all the model component link points, i.e. the lines connecting the boxes in these flow diagrams? This represents the real complexity, as at one level it is fairly straightforward to imagine which model components pass to which, such as an energy input will drive snowmelt, or water that has infiltrated to soil will contribute to groundwater. I won't get into detail on this, but within most hydrological models, each component is its own mini-model or subsystem with an input, output and a storage. In the cases here, we might take energy and mass inputs to calculate a bulk snowpack mass and temperature profile. As the snow heats up, it eventually melts and loses mass as meltwater. This mass of water will be transferred to the next possible node in the model framework. This could be the soil zone, which is also its own temporary storage system with a unique set of parameters that will control infiltration and through flow of water. The model components and transfers could be very simple or very complex, depending on data availability and what we know about the system being modeled. So, complex hydrological models generally require a systems approach. But what do these models actually allow us to do? As humans, we want to make decisions about where we put ourselves or our resources based on the best possible information concerning either the availability of water resources or the avoidance of water hazards. Water is a very dynamic medium, so what it is doing today is not a great indicator of past or future conditions. Models allow us to fill these gaps in our observational data, either in time or space. For example, we may have observed fairly steady fluctuations in the recent data record, but if any elements in the system we're interested in are gradually changing, such as with climate change or land use, then we can't expect water balance or runoff behavior to remain the same. More specifically then, our needs for hydrological modeling address time-dependent planning and management needs, as well as to define the boundaries on spatial development and hazard mitigation measures. And of course, such models can also be used to satisfy our scientific curiosity about hydrological processes. And as examples, here are two water-related hazards that we may wish to mitigate through the simulation of either the temporal likelihood of occurrence, e.g. probability of a flood in any given year, or the spatial extent over which the hazard will occur. The first example is the Calgary flood on the Bow River in 2013. And the second shows a stranded boat in a dried up reservoir in Australia during a prolonged drought. Many tasks then require fairly constant monitoring and short-term prediction in hydrology. Here are some application examples of short-term flow forecasting needs. Most of these will fall into the category of management as they support real-time decision-making processes. During a potential flooding event, for example, the emergency management services will watch the river flow forecasts frequently, as this might inform on decisions on flow holdbacks or releases, temporary floodplain defences, or on evacuation orders. Where land cover, land use, or climatic influences have changed over time and are expected to continue to do so, then we need long-term simulations for planning and policy purposes. Changes in glacier cover and melt at century scale is a situation where provincial governments need predictions to be made at decadal to century scale to inform on water allocation rights. At a municipal scale, simulations can be performed to understand the long-term flow or water quality impacts of floodplain development, channelization, or even floodplain restoration projects. When setting up or choosing a model, it is essential to consider the modeling context, i.e. for what environment, time period, and over what area are the results needed. Sensible decisions over model choice and data requirements cannot be made unless this is clear. For example, will we need to model at the scale of an agricultural catchment or across an entire continent? Are we dealing with Arctic or tropical climates or somewhere in between? Do we have one dominant land cover or many? And do our simulations need to be made at a high resolution time step, such as 1 hour, or over many centuries where even an annual time step may be too fine-grained? Answering these questions will place constraints on the type of model we need and how we set it up to get the job done. The intent of any hydrological model, of course, is to represent the processes occurring in the environment, This can be simple or complex, but there are two fundamental quantities that need to be considered. The first is the volume or mass of water entering and leaving each of the model subcomponents is typically estimated using a water balance approach. And the second is the timing or transfer of water from one model component to another usually requires some form of flow routing. The manner in which these quantities are estimated depends on the space and time of interest and the data that are available to support the simulation. As such, most models will tend to have a fundamental spatial and temporal unit over which calculations are performed. Here we see some examples. In a spatial context, we can either adopt data inputs, outputs, and calculations that represent the entire drainage area of interest, which are known as lumped, or we can distribute our data and calculations through space using either some uniform raster representation of the land surface or an intermediate form of landscape aggregation. Similarly, we can adopt high or low resolution time series data and calculation steps, which will be constrained by data availability and the time step that best captures the processes that need to be simulated in order to obtain credible results. For example, floods occur over short periods and will need a higher resolution time step than evaluating either the impact of long-term glacial ice to water resources or the influence of drought on crop production. So here we have our old friend, the water balance equation again. A water balance is usually calculated for each time step and spatial unit within the modeling environment. All the major processes that we have discussed in the Intro to Hydrology course, some of which are listed here, can be simulated as part of the overall modeling exercise, but whether they are depends on data availability and the needs of the model. The water balance can be calculated for an entire watershed or over a grid or aggregated areas such as hydrological response units. Okay, so just what is an HRU, or a hydrological response unit? To get a more complete answer, please refer to Flugel's paper that accompanies this lecture. But in a nutshell, HRUs are useful as they represent aggregations of land surface areas that have common hydrological attributes such as infiltration, albedo, roughness, land cover, etc. This allows model parameters to be assigned to a handful of land surface units instead of every single grid cell, and thus improves model computation efficiency. So as you can imagine, this is typically a GIS process. And here we see some examples of input land surface attribute layers that can be combined to form HRUs representing common land cover, soil, and terrain attributes. Once the water balance has been calculated for land surface model components, the water needs to be transferred to the next step within the model. Routing can be from water storage to storage or as runoff within a channel system, which is also a form of storage, as any flow entering the channel system must take time to reach the channel end point of interest. We won't discuss methods of flow routing here, but one common approach uses linear reservoirs that are represented by recession constants, which slow down the transfer of flow from one storage to the next throughout the model using a sequence of recession equations. Another popular approach is Muskingum routing, which models flow in a channel as a function of wedge storage along the river reach. Okay, now we know the basic processes of hydrological modeling, let's consider the broad categories of models that are out there. It should be clear that not all environments or modeling needs are the same, and data availabilities in different locations are widely different. Here we see three modeling approaches based on their data and calibration needs. Empirical models are highly calibrated, as they predict runoff response based on historical precedents. Such models are of limited value in a drainage basin that is experiencing changes to its hydroclimatology or land surface attributes through time. Conceptual hydrological models tend to focus on a small number, or maybe one, dominant watershed or hydrological process, and thus tend to be limited in their application domain. Physical hydrological models use the principles and mathematics of physics, leaning heavily on continuity equations and conservation laws. In theory then, such models can be executed with the least amount of calibration, but on the flip side, such models can be extreme consumers of data, both in describing energy and mass inputs to the system and in terms of describing the watershed system through which water must pass. If we wish to perform detailed scenario testing or make long-term forecasts under conditions of a changing environment, then which of these modeling approaches do you think we need to adopt? It should be clear that models come in many different forms, and here is another list of the ways by which we can stratify model types. On the left, we see a roughly temporal stratification into event and continuous models, as well as an acknowledgement that there are specialized models that may not fit into the traditional watershed hydrological modeling paradigm. For example, glacial melt models may require a dedicated modeling framework, as surface runoff from a glacier may not adhere to the typically adopted terrain-based rules of surface water flow that assumes water tends to accumulate downslope. Similarly, karst environments possess surface sinkholes, bypass flows, and the possibility of subterranean flow pressurization that cannot be handled in traditional watershed models. To the right, we see spatial stratifications into lumped parameter or simple input-output models and various forms of distributed parameter models. We have already noted raster and HRU distributions, but other popular forms of spatial model distributions are by elevation, sub-basin, or even by distance from the basin endpoint. The next 4 slides illustrate specific model types of gradually increasing sophistication, distribution, and physical representation of real-world processes. The first example is the empirically calibrated and lumped parameter unit hydrograph approach for simulating runoff at a specific river location for a given upstream rainfall amount over time. The unit hydrograph approach makes many simplifying assumptions about the relationship between rainfall and runoff, such that a downstream hydrograph can be estimated by applying a scale factor and time lag to each unit, e.g. 1 inch or 1 centimeter, of rainfall. Within this simple framework, each unit of rainfall through time can be simply scaled up to generate a complete event hydrograph. Such an approach must be calibrated for a given area using many years of data. While this can be useful to estimate approximate runoff yields and durations for specific events, this approach is not appropriate for long-term simulations or in situations where antecedent conditions, or the watershed properties immediately prior to the event, can vary widely. This next example is still a lumped parameter approach that requires calibration, but now we see some space-time distribution in the modeling steps. The rational method is a conceptual time-area model that ignores process detail and simply models water balance and runoff behavior as a function of isochrones or contours of time. The model assumes that rainfall within a given zone upstream of the basin outlet will incur a predetermined amount of loss and will be retarded by a certain amount on its way to that basin endpoint. Discharge is a function of the area over which rain falls, the intensity of the rainfall, and the loss or runoff coefficient over each region of the watershed. It's fairly easy to calculate, but only of limited use in practice. As the antecedent conditions can change, so will the runoff coefficient. So here we see our first physically based hydrological modeling framework, where key processes of precipitation, interception, evaporation, and infiltration to soil and groundwater are treated explicitly. However, while there is physical realism in this type of model framework, and there is some distribution of flow components amongst watershed storages and flow pathways, this is still a lumped model because there is no spatial distribution. Instead, we see a cascade of mathematical reservoirs from precipitation input to runoff output that represents the watershed as a whole. Such an approach may be adequate for small watershed or in situations of fairly homogeneous land surface attributes with minimal variation in seasonal antecedent conditions, but will tend to perform poorly over larger and more complex regions or over very long timescales. And so here we arrive at a fully physical and spatially distributed model framework. As with the last framework, we see a similar treatment of water balance components, but now we also see the associated calculations are performed for individual grid cells across the land surface. Clearly, this is a much more realistic modeling approach that has the opportunity to better represent important hydrological processes. But, as noted earlier, such approaches can be data intensive and computationally intensive, and therefore require an understanding of the watershed environment that is not readily available. And this can also require that many assumptions need to be made. Consequently, the advantages of embedding spatially explicit process realism can be negated if data do not exist to adequately set up or run the model. Once a model has been decided upon, we need to collect the data to set up or parameterize and to perform simulations with the model. Variables are the input data from which runoff and/or evaporation, etc. will ultimately be calculated. Parameters tend to be fixed or quasi-fixed numerical descriptors of watershed attributes that influence the way inputs are transferred through or lost from the watershed on their way to the outlet. Scanning this list of parameters, you'll probably note that some clearly are not going to be fixed. For example, leaf area index can vary by a great deal over the course of a year. So if your watershed also displays such variation in vegetation cover, then your chosen model must accommodate time-variant parameters. Some models can do this and some cannot, so herein lies one of the challenges of modeling. For pragmatic purposes, we sometimes have to assign fixed parameter values, but in reality the world is more dynamic. Okay, so now we know something about the principles of modeling and different types of models, but how do we go about setting one up and running a simulation? Well, that would be too much to go through in detail here now, as there are lots of off-the-shelf models to suit many different hydrological conditions and scenarios. However, in general, there are 5 major steps. Depending on the nature of the hydrological problem you wish to address, you can either select a pre-existing model, or if your problem is unique or does not require a complex model, you could create your own. For example, simple models can be constructed in numerical and spatial analysis packages such as Microsoft Excel and Esri ArcGIS. Or if you're quite brilliant and have lots of time on your hands, they can be coded from scratch. Once a model is in place, the simulation requires 4 further steps. Calibration, parameter optimization, and validation are often interrelated and even iterative steps to ensure the best possible modeling conditions. Once we are satisfied with the model setup, we can then perform a model run or simulation of the scenario that we wish to evaluate. As noted, hydrological models come in various forms, but here is one example of a modeling interface. This is the freely downloadable US Army Corps of Engineers Hydrological Engineering Center Hydrologic Modeling System, or HEC-HMS. On the left, we see the model component or object manager, as well as a preview of subbasin precipitation input data. In the center, we see the time series plots of precipitation, the associated loss, and the output hydrograph, along with some summary data describing the event being simulated. And at right, we see the numerical data associated with the plot. Many other windows can be entered within HEC-HMS for model setup, simulation, and reporting, and all models will have their own particular interface style. One element to note here is that the discharge is presented as a total runoff hydrograph, and no partitioning of the flow is illustrated. Some models will produce outputs of runoff as well as water balance partitioning within the hydrograph, as we can see here as an output from the UBC watershed model. While this might represent the endpoint of a hydrological model, this is often the starting point of further analyses, such as flood inundation modeling or decision-making processes. The example here illustrates 2 years of simulation on the Bow River upstream of Banff, Alberta in the Canadian Rockies. In this case, the question being asked of the model was, how important is glacier ice melt relative to rainfall and annual snowmelt runoff? Overall, glacier ice melt produced a similar amount of runoff to rainfall, but only a fraction of the snowmelt proportion. Clearly, snowmelt is a dominant runoff component on the Bow, as it is with most rivers in this region. However, the glacier ice melt fraction is critical, as the timing of peak ice melt production occurs when snowmelt and rainfall inputs are reduced. Thus, ice melt elevates flow levels in late summer when the resource is most needed for human and ecosystem services. This has potentially serious implications given glacier ice is reducing throughout the Rockies. While we are able to make observations of glacier recession and runoff, the overall hydrology of these basins is complex with many inputs and outputs. Therefore, we need models to make connections between the many inputs and outputs and to better understand the system. With the enhanced understanding that models provide, we're able to gain knowledge about processes, locations, and times for which we cannot make direct observations. Well, thank you for your attention, and I hope you found these slides informative. Chris signing off.